Most people picture an AI coding agent as a simple loop. The model thinks, it takes an action, it reads the result, and it repeats. Put that simple loop in a production environment, and it breaks almost immediately. The context window fills up, the model gets stuck repeating the same broken command, or an API rate limit crashes the entire process. Kimi Code, Moonshot AI's terminal agent, survives these conditions. It does so by engineering a rigid external harness around the model. This harness relies on 3 nested loops, a single model-agnostic connection point, and operates entirely on the user's local machine, with 0 operating system-level isolation. We can see exactly how this works by tracing the exact path a user prompt takes through Moonshot's TypeScript monorepo. If the harness cannot contain failures or manage state, the raw capability of the model inside it does not matter. This diagram shows what happens when a user prompt enters Kimi Code. It doesn't hit a single cycle. It drops into a structure of 3 nested while loops. The innermost ring is the step loop, called runTurn. This handles the classic observe, act, observe cycle, calling the provider, running a tool, and feeding the result back. It operates under a strict step budget. Wrapping that is the middle ring, runStepLoop. If the inner loop sends a prompt and the provider rejects it because the context window is full, this loop catches the failure, compacts the context, and retries the exact same turn without crashing the system. Finally, the outermost ring is driveGoal. It fires 1 turn per iteration, reading the goal status between turns and driving autonomy until the objective is marked terminal. Outside of these loops, the network call to the LLM gets its own defense. It is wrapped in up to 10 retry attempts with exponential backoff, ensuring temporary rate limits or dropped connections never break the step loop. Separating execution, error recovery, and overarching goals into distinct layers allows the system to absorb and isolate failures before they trigger a complete halt. Inside the step loop, the prompt hits a single entry point called Kosong LLM. This diagram illustrates how that single Kosong LLM socket routes a normalized prompt out to 6 different providers, like Anthropic or OpenAI. The loops never branch to check which model is active. They simply interact with a standardized chat client. Kimi Code forces the model to emit its thinking and tool execution in the exact same step. There is no separate planning phase before action. Before the model even sees the prompt, the harness defends the context window. A process called full compaction triggers the moment utilization hits 85%, guaranteeing 50,000 tokens are always kept in reserve. If a tool returns a massive block of data, anything over 50,000 characters, the harness spills it to disk. It places a small reference inside the prompt, keeping the context window clear of raw data bloat. This diagram shows a vertical context bar designed to maintain speed. The top section, the cache prefix, stays completely static. When the injection manager needs to insert reminders, like a to-do list, it places them below that stable prefix. This prevents the prompt cache from invalidating every step, keeping API requests cheap and fast. The harness aggressively filters, compresses, and structures the prompt to guarantee execution efficiency and prevent API rejection. But Kimi Code lacks physical isolation. There is no operating system sandbox. The system uses childprocess.spawn to run commands directly on the host machine. Bash operates without a command deny list, and path canonicalization is purely lexical, meaning it doesn't resolve symlinks to check where a file really lives. Because the agent runs directly on the user's hardware, the entire safety load rests on a single before tool call gate running a function called evaluate policies. This latter diagram illustrates the permission gate. It is an ordered, first match wins sequence of exactly 19 policies. A tool request drops down the ladder until it hits a matching policy, triggering an immediate allow or deny. This gate has a specific behavior for headless runs. If the agent operates without a user interface attached to approve actions, the system silently auto-approves the tool execution and keeps moving. If a policy rejects a tool call, Kimi Code uses a deny and continue protocol. The model receives a string explaining the rejection, and the step loop forces it to keep working instead of grinding to a halt. If the model gets stuck calling the exact same tool repeatedly, a streak detector intervenes. At streak 3, it injects a reminder forcing the model to articulate what new information it expects. If the streak reaches 12, the harness forcefully terminates the turn. An agent can operate securely on a host machine without containerization, provided its permission pipeline rigidly orders approvals and explicitly blocks specific threats like sensitive files and internal subnets. Once a step concludes, Kimi Code has to store the results. It does not use a vector database or a tiered fact store to maintain memory across sessions. Memory is an append-only, event-sourced journal saved directly to the file system. It records about 30 specific event types, like prompt updates or permission changes, to rebuild state. This reveals the second major architectural gap. There is no programmatic verification running inside the loop to confirm a task is actually complete. The definition of done relies entirely on the model's self-attestation. The loop ends when the model decides to call update goal with a status of complete. A goal can include a completion criterion field, but it is just free-form text. The harness never executes it as a test or checks its logic. The three loops and permission gates exert total control over execution and failure states, yet the final output relies completely on the language model accurately judging its own work. A production agent is defined by its physical boundaries: the step limits, the transport retries, the context compactor, and the permission policies. Ultimately, the raw intelligence of the model inside is secondary to the heavy external architecture that keeps it running.